So in the last video, I said that I was going to go through and prove that the area underneath the normal distribution is equal to 1. And ultimately, how I'm going to prove this is, given the definition for the normal distribution here, I'm literally just going to take the integral over the range of negative infinity to infinity of the normal distribution to determine its area. So before I go through and do that, though, I want to take a little side discussion. There's going to be some details in evaluating this integral that I want to cover beforehand in their own videos. So that's what I'm going to cover now, is some proofs that I want to show you that is going to be useful when we ultimately get around to evaluating this integral. So let's take that detour now. If I scroll down. Okay, so what I want to prove to you beforehand is that if we have two functions, f of x and g of y, if we take the definite integral under f of x and multiply it by the definite integral over some range for g of y, it's the exact same thing as if we just tried to evaluate the double integral of both of the functions. So in order to prove that, let's set some ground rules or some terminology in which we can communicate. I'm going to call this the left-hand side, and I'm going to call this the right-hand side. And what I'm ultimately going to do is I'm going to evaluate both of these integrals, and we'll see that once the integrals have been evaluated, that they are indeed, in fact, equivalent. So let's get the left-hand side here real quick and drag it down. Okay, so this is the left-hand side. And what I'm going to do is I am going to just go ahead and start evaluating this integral. And assuming that, some antiderivative exists for f of x, I'm going to call that antiderivative capital F of x. Okay? And I'm also going to evaluate the endpoints, so that would be capital F of b minus f of a. Okay? And if I were to do it for g, I'd get something that looks very similar, right? I'd get capital G of d minus g of c. Okay, I'm going to stop there. Now I'm going to pull the right-hand side equation and move it down. So now that I got the right-hand side equation, let's do this. RHS, clean this up a little bit. Okay, and now I'm actually going to go through and evaluate this integral now. So when you're doing a double integral, you can see that we're first integrating with respect to y. So I can actually pull f of x outside of this integral because we're not integrating with respect to x, we're integrating with respect to y. And this function is defined only as a function of x. So let me go ahead and rewrite this with having pulled f of x outside of the first integral. So this now becomes the integral from a to b of f of x times the integral of g of y, g of y dy. Gotta make sure to keep the bounds on these integrals, and this is still dy dx. So I'm actually going to go through and evaluate this part here. Okay, so in the next step, we see that this is still the integral from a to b, f of x dx, and then we have g of d minus g of c. Okay, and now since we're only integrating with respect to x, and this is now essentially just some constant, I can pull this outside of the integral. So now if I rewrite this, this now looks like g of d minus g of c times the indefinite integral from a to b of f of x dx. Okay, and now we are just going to evaluate this integral over here. So moving on to the next line, we have g of d minus g of c times the integral, or I'm sorry, not the integral, times f, capital F, of b minus f of a. And now we can see, right, we have now proven that the right-hand side, which was we ultimately evaluated to be equal to this, and the left-hand side, which we ultimately evaluated to be equal to this, well, the two things that I just underlined are the exact same thing. I mean, they're out of order, but the ordering of the multiplication does not matter. So there you have it. This statement has been proven to be true, that if we have two functions and those functions are defined as different variables, like this is a function of x and this is a function of y, we can rewrite it as its double integral, or we can go backwards. We can rewrite it as two separate integrals. Okay, we're one step closer to being able to prove that the area underneath this curve is equal to 1. See you in the next video.